And while you can describe jet production or also the production of light particles or even D mesons and B mesons at large transverse momentum, you can describe this easily with factorization theorems. Since long time, people have several difficulties to describe the quarkonia production. So you have different models, you have also factorization theorems, and presently the difficulties is to describe at the same time the transverse momentum dependence and also the polarization observables, and also there are some complication with the production of a pair of Jpsi. So here, just to remind that you have a different model for the production of Jpsi or even quarkonia. So today I will present, I will say more about the color evaporation model. But here the idea is that you produce a Q-bar pair, and then you have a lot of soft gluon emissions, and then the quantum state of your quarkonia can be different from the quantum state of the perturbatively produced Q-bar pair. Then on quite, it's nearly exactly the opposite idea. You have the color singlet model, where here you want the Q-bar pair to be produced exactly in the same quantum state than the Jpsi, for instance. So it should have the same spin, the same, it should be color singlet, etc. And also you have the NRQCD, non-relativistic QCD, which includes both color singlet and color octet contributions. And I will say more about this in a few seconds. And that's basically these three main models. And they are all based on some factorization hypotheses, even if it's not always explicitly stated. Okay, so for instance, there is a quite interesting paper here where the authors here they compare the color evaporation model and NRQCD. So the idea is that generally these two models are presented as being very quite different, but in fact you can present the color evaporation model let's say with the same formalism than NRQCD. So the idea is that the cross section can be written like that, where H is the quarkonia state. So in our case, H will correspond to a Jpsi, and then you have a sum on all possible Q-bar quantum state, okay, like spin, color, etc. And you have a convolution, a product of a short distance coefficient to produce this Q-bar pair in the quantum state n, with non-perturbative functions, which in case of NRQCD are called long-distance matrix element, to transform this Q-bar pair into the quarkonia H. Okay, and basically the difference between NRQCD and color evaporation model is that NRQCD they fit these non-perturbative functions on data exactly. I mean, similarly to what is done for pattern distribution functions, and while in the color evaporation model they just assume that these non-perturbative functions are all the same. So basically, in the color evaporation model, you have just one non-perturbative parameter, and this is the main difference. And also, the goal of this author here was to show that the color evaporation model is not really correct, because when you use non-relativistic QCD, thanks to something which is called the heavy spin symmetry, you can relate some of the large distance matrix elements. And the relation is not trivial, and it is violated by color evaporation model, which is the reason why, from the theoretical point of view, this model is not really considered to be a good model, let's say. But still, it is very useful which is the reason why I did the work on it. It is interesting for several reasons. So first, it is really simple to implement. Okay, the implementation is based on this equation, where here this is the differential cross-section for the production of Jpsi with transverse momentum Pt. You have the non-perturbative parameter here, f Jpsi, and then you just integrate the differential cross-section on the invariant mass of the QQ bar pair between 2 times the charm mass and two times the D0 mass. So it's very simple to implement, which is one of the advantage. And also it has it provides quite good description of the data. So it's good for some kind of quick phenomenological studies or something like that. Sometimes it is used by some group as a upper limit on the true quarkonia cross-section. Okay, if you want, you can also use the improved color evaporation model, which is basically it's quite similar. The two differences is that here, instead of 2mc, you have the mass of of the quarkonium of interest. So in our case, it will be the mass of the Jpsi. If you are working with a psi prime, then you will put here the mass of psi prime, etc. And also, as you can see, you have a rescaling of the QQ bar pair. So the momentum of the Jpsi is not exactly the same than the momentum of the QQ bar pair. And this modification helps a bit to describe the transverse momentum distribution of a ratio of quarkonia cross sections. Okay. So as I was saying, this model gives a relatively good description of the data, in particular for integrated cross section. But if you work at next leading order, still you have a quite a big issue that at a large PT, you have a significant overestimation of the cross section, as you can see here. So here, this is a comparison of color evaporation model at next leading order compared to Atlas data. And you can see that you have something like a factor 4, an overestimation of a factor 4 of experimental data. So this plot has been taken from this physics report. And the main issue comes from this kind of diagrams, which scales like 1/pt to the fourth, and it is too hard. So basically, the main goal of our study was to try to solve this issue. This is the main goal, basically. So solve this issue. And also, we will use a transverse-momentum-dependent formalism, which is called KT factorization. And here in this formalism, instead of using collinear pattern density, you use an integrated pattern density. And also, I will show that this kind of data could help to constrain this unintegrated pattern density. But our main goal is to solve this issue at large PT. And so our proposed solution is simply to take into account the evolution with the factorization scale, because as you know, all non-perturbative functions in QCD should be generally they should be renormalized, and then you introduce a dependence on a factorization scale. This has been studied it has been studied by several people, but for some reason, this evolution of the QQ bar pair, this evolution with the factorization scale, has not been used in the extraction of non-relativistic QCD large distance matrix element, or in the case of the color evaporation model. And so I will show that if you simply implement this scale dependence, then you bring the calculation in agreement with data. And so basically, the conclusion of our study is that there is a significant effect of the scale evolution, and then it should also be taken into account by studies using NRQCD, and in particular, where different groups are working on the extraction of large distance matrix elements in NRQCD, because sometimes they work with inclusive data, and sometimes they work with high PT data, and so it corresponds to different scales. And so it is not completely surprising that there are some So what they see is that this set of large distance matrix element does not really agree. There are some tensions, and this is maybe not surprising. Okay, just to mention quickly the formalism. Just to mention quickly the formalism developed by Kang, Ma, Q, and Sterman. So basically, what they do is first they separate the cross section into the leading power, which scale like 1/pt to the fourth, and next leading power contribution, which scale like 1/pt to the sixth. So the cross section for the quarkonium production is given either by this kind of formula for leading power, or this kind of formula for next to leading power. So in this case, you just produce any pattern F, for instance, let's say up quark, and then you have a fragmentation of this pattern F into the quarkonium. And at next leading power, you produce directly the QQ bar pair, and then there is a fragmentation of the QQ bar pair into the quarkonium. And okay, so as usual, these fragmentation functions obey some evolution equation. So this is the evolution equation for the fragmentation of pattern F into quarkonia, and this is the evolution equation for the QQ bar pair into a quarkonia. And you can see that the effect of the evolution of the QQ bar pair is that you mixed the quantum state. In particular here, because you have a splitting of a QQ bar pair with a quantum state n into another QQ bar pair with another quantum state kappa. Because, for instance, you have an emission of gluons. Okay, in our case, our calculation with the color evaporation model just includes some of the leading power, but not all of them, because basically we do not take into account this kind of contribution where you produce any pattern F, and then the pattern F hadronized into quarkonium. Okay, so this is our main, just one slide to present a bit our formalism. So as I said, we use a transverse momentum dependent formalism, which is called KT factorization. So here, this is a typical equation for KT factorization. So the cross section is given by the convolution of an integrated pattern density. It's called unintegrated because it depends on the initial transverse momentum of the pattern, K1t and K2t. And this sigma hat QQ bar should, in principle, be the off-shell cross-section to produce a QQ bar pair. In our case, in fact, you use some kind of hybrid formula where the cross-section here is not off-shell, but on-shell. And one of the reasons for this is that if you work with an off-shell cross-section, basically you can only work at leading order because the next leading order is not available. And this kind of hybrid KT factorization has been used already for other observables, for instance, for the Rayleigh. You can see here a reference, and you can see that it works quite well. So what we do is first we produce at short distance a QQ bar pair like this, and then one of the interests to work with a transverse momentum dependent formalism is that if you work with collinear factorization, then at leading order, the transverse momentum of the Jpsi is necessarily equal to 0. So it contributes to the integrated cross-section, but it does not contribute to the differential cross-section. But in our case, because the initial transverse momentum of the patterns is not 0, then you can produce, even at leading order, a Jpsi with a non-zero transverse momentum. The next leading order cross-section has been computed with a math graph. Okay, so it automatically includes all diagrams and the subtraction term to avoid double counting and infrared divergences, etc. And once the QQ bar pair is produced, then we start to evolve this QQ bar pair, and the evolution is done approximately by using the typical time-like pattern shower. So in our case, we use PTSAs. beta 6. And okay, and some details. So when you use a time pattern chamber, you need to choose the initial scale. Okay, and which we did a standard choice, which is to choose the initial scale mu I equal to the factorization scale equal to the renormalization scale, and all these scales are chosen to be equal to the transverse mass, which is the square root of pt square plus the mass square of the Jpsi. Okay, and then during this evolution, during this time-like cascade, the virtuality of each heavy-quarks will decrease, and when you reach a scale of the order of the Jpsi mass, then you apply your hadronization model, which in our case is the color-evaporation model. And we choose the non-perturbative parameter equal to 0.014. So it is a value again taken in this physics report. So in that sense, our calculations are parameter free. Okay, and so just to mention, so here this is a picture of the QQ bar evolution. So here we produce a QQ bar at next leading order. So there is a charm, anti-charm, and also a gluon. And then the time-like cascade will perform this kind of evolution. You have emission of gluons, etc. And then when the scales of the charm and anti-charm is around the Jpsi mass, here we apply the color evaporation. And so one of the consequences of this evolution is to mix the different quantum states, and in particular, it mixed color singlet and color octet states. And also, since the initial scale is proportional to the transverse momentum, or more precisely to the transverse mass, so if you have a higher transverse momentum, you have a longer cascade, and then more emission and more energy loss. And so what you expect is that at a large transverse momentum, you will have a larger shift to the left, while at a small transverse momentum, the shift will be smaller because the cascade is shorter. Okay, so this is the expectation, and this is why you can expect that this kind of effect will soften the NLO fixed order calculation. And so now this is the result. So in blue, these are atlas data. So it's exactly the same data which are in black here. And in red, it's our calculation. So with next leading order cross section and this time-like cascade. There is also the effect of initial transverse momentum, but at large PT, it's not really relevant. And so you can see that basically it brings calculation in very good agreement with data, except maybe here, but it looks like a statistical fluctuation. So basically, we could nearly stop here and say that the issue is solved. So the idea is really that this evolution, it's a prediction of perturbative QCD. You cannot avoid it. Okay, if you compute the cross section at NLO and then at next leading order, etc. So if you increase the order of calculation, then you will have more logarithm and more logarithm, and these logarithms are reasoned by this kind of a time-like cascade or evolution. So it's a prediction of perturbative QCD, and you need to include it. And once you do it, you find that there is basically no real issue. There is no more issue. But it does not mean that the color evaporation model is a good model from the theoretical point of view, but at least still it kind of works. Okay, and also to show the result and to comment the result at small and intermediate PT. So in this region, the initial transverse momentum is important. So here is just a plot without data, again for the transverse momentum dependence of the Jpsi cross section. And you can see in red and in blue what you obtain if you use two different unintegrated PDF sets. And in green, it's what you will obtain if you use a collinear factorization. Okay, so you can see that in this range, let's say for a PT smaller than 8 GeV, the initial transverse momentum is very important. And as I said, also, if you use collinear factorization, leading order does not contribute. So this green line is also equivalent to pure NLO contributions. So you can see that the cross-section is dominated by leading order cross-section for small PT. And then when you reach a PT of around 8 GeV, then you see that the next leading order diagram start to dominate the cross-section. Okay, so these are some of our results at small and intermediate PT. So here again, in red, it's our calculation, and we compare this to ALICE here in blue and to CMS data in green. Again, we have a good description of data, let's say when PT is larger than 10 GeV. And in the opposite, you can see that at small PT, even if we are in agreement with data within uncertainty, our central value underestimate the data. So these are calculations for data at 7 TeV. We have something similar for LHCb. So now it's at forward rapidity, but the same conclusion. When you reach PT of 8, 10, it's okay. And below that, it's in agreement with data within uncertainty, but our central value underestimates the data by maybe a factor of 2 or something like that. Okay, and so you can also discuss the universality of Jpsi. So universality means that it's independent of the energy of the collisions. And in our case, we always use exactly the same value. And you can see that if you look now at the results for LHCb data at 13 TeV, and also to Phoenix data at 200 GeV, the results are comparable. So we can say the same quality description of the data with the same value of the parameter Jpsi. So our conclusion is that indeed Jpsi is universal. And it was expected because this is also the result found by people working with collinear factorization. But it is also interesting to look to other calculation with KT factorization. So here this is a plot obtained by this author in this paper. In their case, they use a true KT factorization calculation. By true, I mean that they use leading order of shell cross-section. And also they are working with the KMR UPDF, so Kimber-Martin-Riskin UPDF. And you can see that the result is quite, I would say, quite good, even if, I mean, basically they are in agreement with data within uncertainty. Still, their calculation looks a bit too hard. So maybe it could be related to their choice of an integrated PDF. Maybe another set of an integrated PDF will do the job better. But what is more interesting is that here they use this value of Jpsi, but at 200 GeV for Phoenix experiment, they have to use a value which is about 10 times larger. So in their case, they found that Jpsi is not universal. And so I have an hypothesis to explain that. And in fact, it's related to some small project I am currently working on. So just to explain this quickly. So it's interesting to compare the KT factorization with TMD factorization. So for instance, if you look at DIS or CDs, and if you are interested by the structure function, this is the equation for TMD factorization. If you compare with KT factorization, in case of KT factorization, you have only the first term, which is usually called Y term, while the second one and the third terms are completely absent in KT factorization. But the consequence of this, the main goal of these two terms is that it reduces the scale uncertainty, and also they give an important contribution at large Birken X. So KT factorization was designed for small x, So maybe it's not really a big deal to neglect these two terms. But the main difference between TMD and KT factorization is the treatment of this first term here, the Y term. So in TMD factorization, when you want to compute the structure function integrated on KT, they perform the integration up to infinity. They have some UV divergences, and so they use renormalization. And basically, this procedure is equivalent to cut the transverse momentum integral at Q square, where Q square is the Hertz scale. So in our case, in the case of Jpsi production, Q square will be PT square. Okay. In the opposite, in KT factorization, you simply cut the integral at a large scale, typically S, which is the Mandelstam variable for the proton-proton collision, for instance, or for the electron-proton collision. Okay, so the consequence of this is that if S is much larger than Q, you will overestimate the cross-section. And this, it's really easy to see. So for instance, in my case, I'm just doing some calculation in the Yukawa theory, comparing with another paper which did the same thing for TMD factorization. And you can see that indeed, if you integrate the cross-section up to S, you overestimate the structure function. But if you cut the integral, the transverse momentum integral at Q square, then you get a correct result. And then the consequence of this is that if you really do the integration in KT factorization, if you really integrate on KT up to S, then now the choice of your unintegrated PDF really matters. And now I will explain why it will be clearer why I'm explaining all this. Is that let's consider that now you are interested by Jpsi production, and you look at a fixed PT. Okay, so if you are at small energy, the integration region where you integrate from PT to S is not that large. And okay, so you have not a large overestimation of the cross-section. But now, when you keep PT fixed and you increase the energy, this region starts to be larger and larger, and you get a larger and larger contribution to the cross-section. And to compensate that, you need to reduce the value of Jpsi to be able to describe data. And so this is exactly what they found here in this paper. They found that Jpsi decreases with energy. And in my opinion, this is because when you work with KT factorization, you do the integration up to S instead of doing the integration up to Q. And in their case, because they work with this kind of PDF, which has this 1 over KT square contribution, then even for large transverse momentum, for large KT, the contribution is not negligible. In our case, even if we do the integration up to S, we use a pattern branching PDF, and the specificity of this pattern branching PDF is that the contribution, their contribution in this kinematical region is completely negligible. So effectively, it's equivalent to cutting the transverse momentum integral up to Q. So all this to say that apparently the universality of Jpsi and also the transverse momentum shape of the Jpsi cross-section could help to better understand an integrated pattern density and also KT factorization. And that's all. So, but the main point was to say that once you use the color-evaporation model at next leading order and you include the scale dependence of, or if you prefer, if you include the Q-bar evolution, then you get a good agreement between calculation and data, in particular at a moderate and large PT. It's not clear what is the consequence of this for the non-relativistic QCD large distance matrix element, because in some case, these LDME functions are negative, and sometimes people working with NRQCD, they get negative cross sections. So maybe including the evolution in the extraction of this function could help to solve this kind of issues. And okay, as I said, both the differential cross section and the universality of Jpsi could help constraining unintegrated PDF. That's all.
Thank you very much, Benjamin, for the very nice talk. Question from the audience?
May I ask a question?
Yes.
Actually, I think comparison with data cannot be treated as a proof of a model. It's test of the model. First of all, the model must be justified theoretically, and then you test it, because if you have data and you are free to invent any models, amount of models which will describe this data well is infinite. And example is, for instance, same physics report review by Philip Landsberg. Actually, besides color singlet model, it was his and Stan Brodsky paper where they calculated higher order corrections to the color singlet model, which is orthogonal to color evaporation model and much better justified. And they also claimed it well describes data. So description of the data, I would never buy as a proof that model is correct. Yeah,
no, for sure.
I agree. Yeah, I have never seen any justification why color singlet model they integrate between mass of Jpsi and two masses of D meson. Is just some intuitive feeling. There is no proof, just ad hoc.
No, for sure. But so the same for I don't know, an NRQCD or color singlet model, where they use basically a delta function. But it's also hard to believe that to produce a Jpsi, you need to produce a Q-cuban state which has exactly the same mass, when you know that there are some evolution and everything, so it will be, so it's also hard to believe. But in any case, the main goal of this study is not to say that the color evaporation is correct. The main goal is really to say, okay, this is what we have before including evolution, and this is what we have after including evolution. So the evolution of the Q-cuban pair is really significant. It changed at large PT, it changed the cross section by a factor of 4. And so since this evolution is not taken into account in the extraction of large distance matrix elements in NRQCD, and since there are some tension between different sets of large distance matrix elements, depending on if they are extracted at small pt or large pt, probably including this evolution, in particular for groups working with large pt data, will help to solve this tension. So it's mainly just a tool. Here, the color-evaporation model is just a tool to say, okay, this evolution looks really important, but still, of course, it's also useful. I mean, even if the color-evaporation model is not really justified from the theoretical point of view, it's useful when you want to do some quick study or something like that.
Okay, thanks.
More questions, comments? Marat, please. Marat, you're muted. Activate your microphone.
Can you hear me?
Yes,
Yes.
now we hear you.
Okay, thank you. Benjamin, actually, I'm somewhat confused with your procedure. First of all, I haven't seen your definition of this factor Jpsi, which appears in front, and as far as I understand, which is crucial for description of the data. First, it appears in slide number 4, yes, here. And when you consider leading order, I think it doesn't matter a lot. It's just phenomenological constant. But when you start playing with next to leading order corrections, then it's I think necessary to define it in terms of matrix elements, and especially when you discuss its evolution. Could you please comment a little bit on this?
I'm not sure to understand fully your question, but yes, I mean, so in NRQCD, you have a lot of non-perturbative function like that. And in the color evaporation model, you have just one, which is related to this Jpsi. And so everything which is true for PDF, let's say, is also true for this kind of functions. So their value depends on the order of calculation, etc. So if you work to leading order, then you need to fit data to determine Jpsi, and then if you work to next leading order, you need to fit again, because this kind of non-perturbative parameter depends on the order. It probably depends also on some schemes you use for renormalization, this kind of things.
I think here is my detail which I do not understand very well. In MQCD, you basically end up with an infinite set of different matrix elements. And you now claim that in color evaporation model, you basically assume that there is just one, which is dominant, and which is.
I mean, you have the same infinite set, but all are equal.
Understand your point. And I'm also concerned with the procedure. As far as I understand, you fix this Jpsi from the same data which you try to describe. Is it correct?
Not really. So in our case, we didn't fit Jpsi. I just took the value from the physics report by Landsberg. And typically, people, they fit Jpsi from low energy data, and then they apply to larger energy data. You can fit it also for integrated cross-section and these kind of things. But to be honest, I'm not sure this value I'm using, and which I found in the physics reports by Landsberg, I'm not sure exactly, I don't remember exactly how we determine this value, but in a case, this is just a normalization factor. So here the main issue is not the normalization, it's the shape in any case.
I understand. And the last question, I wonder if you, as far as I can see, you have shown that you can describe PT dependence, and I wonder if you can describe rapidity dependence.
It's a good question. So you mean integrated on some range of PT, and then
for example, either integrated by PT or maybe for some fixed rapidity at central rapidities. There are different data from experiments available now.
At least, for instance, for Atlas data, you have a lot of range of rapidity, which are not shown here in this presentation, but we put all the plot in the paper, and the description of data is quite similar from central rapidity to forward rapidity. Even if I think that at forward rapidity, it's maybe working a bit less. It's not that good, but still it's good. So I would say that also the dependence with the rapidity is quite good, but maybe not perfect.
Okay, thank you. That's all.
Thank you, Marat.
More questions coming from the audience? If there are no more questions or comments, we send the speaker again. We send Benjamin for the very nice talk, and we meet at the next seminar. Goodbye.
Okay, thank you. Goodbye.
Thank you. Bye.